One of the best way to solve this equation, believe it or not, is by guessing. In a previous video about oscillation, I explained how to solve this equation by using algebraic manipulation first and then by direct integration. In this video, I'll show you a different way of solving this equation, and that is done by the method of guessing. And even though it looks like a silly way to solve a differential equation, but it is actually very useful not only just to solve this equation, but to solve a whole class of equations. And that special class of equation is called linear homogeneous differential equation. So this name needs a little bit of justification. So first of all, the equation is linear because this equation does not carry any term which has x squared or x cubed or x dot squared or x double dot squared or x dot x, etc. That means all the terms in this differential equation are linear. And then the next word is homogeneous. What homogeneous means is that all the term contains x, right? The derivative is carried out in terms of t, so this is the differential operator, so this is denoted by dot. And so it is fair to say that the independent variable in this equation is t. T is the independent variable. If there is any term which contains t only, but not x, then this is a homogeneous equation. So this would be an inhomogeneous equation if we had a term on the right hand side which is purely a function of t. And this function, which purely depends on t, is called the source term. Since in this equation this term is 0, then this equation is called homogeneous differential equation. If this were non-zero, then this would be called a linear inhomogeneous differential equation. In this series of videos, we'll be discussing both of them, and fortunately it is possible to find out the general solution to the inhomogeneous differential equation, which will come up at the later part of this series. So as I was explaining before, this equation is called the linear homogeneous differential equation, and we'll be solving this equation by using the method of guessing. But it's not just any type of guessing, it's not arbitrary random guessing. This will be the process of educated guessing. And even though we explain this trick based on this equation, but to a great extent this process will be applicable for almost every type of linear homogeneous differential equations. So in order to motivate this process, we rewrite this equation in a different way, which is like this: x double dot is equal to minus omega squared x. And if we write this equation in its fullest form, this looks like this: the second derivative of x with respect to t. Actually, let me write this x here as if this operator is acting on this function, and then I'm getting some constant times the same function. So now this gives us a different type of question. the solution is now being found out by using the functions who, when being differentiated, gives us the same function. So the candidates should be functions such that their derivatives gives us the same function, and we do know this type of functions, and they're called the exponential functions. Precisely, d dt acting on e to the power t gives us e to the power t back. But now we don't have just the function, we also have some constants in front of it. So we have to modify this function in such a way that accounts for these constants, and that will be our solution. So in order to accommodate that, our candidate solution becomes x equal to e to the power some constant times t. So this is our candidate equation, and if we differentiate it once, this is equal to x dot, this gives us differentiate it again, you get x double dot equal to r squared a to the power rt. So if we plug those into our differential equation, we get r squared a to the power rt plus omega naught squared a to the power rt. This gives us 0. So because e to the power rt is not 0, we can eliminate it from this equation by dividing the equation by e to the power rt, and this becomes r squared plus omega naught squared equal to 0. So now this equation have two solutions, r equal to plus minus I omega naught. So it's a second order differential equation. It's supposed to get two solutions, and so our solution functions are going to be e to the power I omega naught and a to the power minus I omega naught t. Here we have t as well. And from the property of linear differential equation, if we have two functions f and d, both solutions of a linear homogeneous differential equation, then of course their linear combination, which is a constant times the first function and then another constant times the second function, should be a solution as well. And so therefore our solution becomes x equal to a constant a to the power I omega naught t plus another constant b e to the power minus I omega naught t.